Greetings, class. It's so good to be with you again. This is Whitlock and Schluter Chapter 15. It's called ANOVA, which stands for Analysis of Variance. We're going to do it in two parts. First off, I want to focus in on the theory. Second off, I want to work through the book example. Despite saying that, I think it's most instructive to just have an example in our mind as a background. So we're going to do the book's example here. Now, it's the knees who say night. We won't read the whole thing, but the idea is that they wanted to test people's circadian rhythms. An experiment was designed with 22 subjects. They were broken into 3 groups. There was a control group who didn't receive any treatment. There was a knees group whom they woke up at night and they shined light on the back of their knees. And then there was an eyes group where they woke them up and they shined light in their eyes. And they wanted to see if the treatment had an effect on shifting their circadian rhythm. Okay, so that being the case, we're going to have 3 groups. There's a mean shift for each group, and we're interested in whether or not those means are the same. So here comes ANOVA then. Okay, it's called ANOVA, and ANOVA stands for Analysis of Variance. That's where the things come from. We have G groups, and we're interested in comparing the means of each group. So this is a hypothesis test. It's a classical hypothesis test, and the null hypothesis is the mean of group 1 equals the mean of group 2 equals the mean of group 3, and so on, all the way up to the Gth group. All means the same. So all means are the same. Now the alternative then is simply mu1, or excuse me, mu i's are not equal somewhere. Okay, just any 2 of them are not equal. It doesn't specify which 2, it's just somewhere there's a difference. Okay, it doesn't specify how. They're either all the same or they're not. That's the null hypothesis. Okay, so of course we select our alpha in step 1, and then in step 2 we're going to collect the data. So we're going to get data, and of course we're going to calculate the sample means. So we're going to get the x bar i's. We're going to calculate the sample standard deviations. Okay, so the sigma i's. I could put a hat on those. I guess I could put S. So the sample standard deviations. Collect all that stuff, and what we roll into is an F statistic. Okay, that's what we're after. And the F statistic turns out to be this interesting thing: mean squared error, mean squared groups divided by mean squared error. And I'll come back to that in a sec. That is our ultimate test statistic. Now, let's see here. Okay, good. The diagram for this. Okay, the F distribution. So F follows an F distribution. F is named after R.A. Fisher. He was the one who discovered this. He didn't name it himself. It was named after him later. It has 2 degrees of freedom. The reason for that is the mean squared group and the mean squared error both follow a chi-squared distribution, and the quotient of chi-squared random variables follows this F distribution. Okay, so it's still, since these are made out of squares, starts at 0. and it's always skew right. So it kind of looks like the chi-square distribution. And the question is, if we're too far to the right, we're going to reject the null. If we're closer over to the left, we will not reject the null. Okay, so what is really going on here? All right, let me just finish the test and then get into the details. So we're going to have a situation. If the p-value is, of course, less than or equal to alpha, then we reject. That's always the case, what we've always had. That's equivalent to the following. Let's take a cutoff here. We're going to have a critical value, so I'm just going to call it f critical. And we could put, if we want to, we could put it at the level alpha. And so if alpha was 0.05, then we would have this 5% upper tail, and the critical value will cut that off. So this rejection on the p-value is equivalent to if the f statistic is greater than or equal to f critical alpha, then we reject. Okay, for example, if our f-stat turned out to be over here, then we would have a value, a p-value less than alpha, and our f statistic would be greater than alpha, as you can clearly see on the graph. Awesome. Okay, so I guess that gives us our decision here, and I think that's what we need. Let's just note that rejection of the null hypothesis implies there is at least one difference between population means but it does not specify which ones. Which. Okay, to get at the which, we're going to have to do a subsequent test. Okay, so that's the baseline. Now, what's going on with this f? How do we compute this? Let's go into that a little bit here. Okay, so here's the idea. The idea is we're going to collect our data, and if you do a calculation, then let's just suppose that this gives us our x bar, and that'll be our grand mean. So grand mean. That's the mean of all the data. But if you take group 1, I'm just going to map group 1, let's say right over here. Okay. Group 1, and we're going to have an x bar 1. Maybe this is the control group in our light experiment. And we're going to have another group here. Another curve. Okay. Here's an x bar 2. Okay. Maybe that's the light group. Okay. And you'll notice that the data points for x bar 2 are bunched differently than the data points for x bar 1. Okay. They certainly have different means. The overall mean is between the two of them. And so we're working like this. The mean squared error is going to be based upon the data from group 1. All these data points are distant from its mean. So you'll have, and think of the mean squared error as a sigma. Okay, it's just a measure of variation of the data in group 1. And again, there's data points for group 2. They all vary from the mean by a certain distance here. We can measure that. Mean squared error incorporates both of those within the group. It's the book calls it group mean square. Okay, that's the basic error or variation in the process. Now, there's another variation. And that other variation is this mean to the grand mean and this mean to the grand mean. If there was a third group, like we have in the example, I could sketch out another curve. Okay. Maybe it's closer into the middle of those, maybe not. But again, I'm going to have these points. They all have some distance from the center. Okay, there's going to be a sigma, which will go into the mean squared error. But this distance here is again a mean of the third group to this grand mean. And those means give us a mean squared error. Okay, mean squared error, all three of these lines. Okay. And so here is the result. F statistic is the mean squares of the groups divided by the mean squares of the error. And this is as follows. If it's greater than or equal to 1, that implies population means are different. If it is less, well, let's put greater than. If it's less than or equal to 1, that means the population means are the same. And this is because if these groups are far apart from one another, then that is inserting a lot of variation into those means. It's going to be greater than the amount of variation within each group itself. That's the error within the group. So that's our basic sigma. And so in the theory, that is the quotient that we're after. And so if F is too big, how big is too big? Well, we measure it on this distribution right here. Then we reject the null hypothesis. Okay, that lays out the basic steps of ANOVA. Afterwards, we'll look at an example.